it's in the afternoon, so I recognize after having so many intense talks on philosophy and biochemistry, it would make sense to give you a lighter talk, less intense science, make it a bit more accessible. Unfortunately, I guess the term is the spirit's willing, but the flesh is weak. So this again will be another technical talk. So I wish you well. Today we'll cover a really light topic. It's going to be origin of life, thermodynamics, and design. So thermodynamics is a sort of word that puts terror in the hearts of you that don't like science that much, but don't worry, I'll make it accessible. And some of the material will be a little technical, but don't panic, okay? Remember, don't panic. We'll bring it back down pretty quickly. So the challenge in a diverse audience is some of you are scientists, so you're expecting some pretty rigorous arguments, and others of you may be in other disciplines who may not want as rigorous of an argument. So I'll kind of go up and down. So hopefully I won't terrify you or bore you at the same time. But just to give you the discussion of the origin of life is really significant because we've been talking about the evidence of design in nature. And the question is, where is that design? And this morning I made a case that you see enormous amounts of design in the origin of our universe, the laws of physics, the laws of chemistry, the design of our planet, and so forth. And the question is it the case that God could have designed everything at the beginning in such a way that everything could have happened naturally, perhaps with little tweaking behind the scenes, the origin of life, evolution, and so forth? And absolutely that's what God could have done. But there's a problem. As I'll argue, if the laws of nature were designed to allow for the production of life, those laws would be so complex and intractable that science would be impossible. So to do science, you have to have a set of simple, accessible laws. But simple, accessible laws do not create complex machines. So again, the metaphor often used is that nature is like a machine. You set up the machine, you wind the clock, you let it run. That's the wrong metaphor. The metaphor is that of a musical instrument. Nature was designed to allow for life to exist and flourish, but nature was designed to interact with the designer. So what you see throughout life is evidence of a designer infusing information into the system. In fact, that makes sense. Any of you artists in here? What am I saying? It's a science conference. That's cool. I'll talk to the band afterwards. But if you ever happen to meet an artist, invite them to the conference. It's not so bad, but besides that, and you ask them, how many artists do you know that want to create one piece of art and then stop? Don't artists like to create lots of art? So one thing about God is an engineer, but he's also an artist. So he likes to create diversity. So artists don't create machines to generate art for them, they create it themselves. And that's what you really see with life is like the production of both an engineer and an artist. And where that is most clear is at the origin of life. Because what you find is science for several centuries has accepted what's called scientific materialism. That's the idea that you can only explain things in terms of the laws of physics and chemistry, natural processes. You can't argue that there is design in nature. And the origin of life is a lot like when Galileo looked through the telescope and when he saw planets that were orbiting or he saw celestial bodies in motion, he knew the geocentric view of the world was going to come to an end. He knew that the view that our Earth was the center of the universe had to be false. And it took time for that to spread through the scientific community, but that's what you see with the origin of life. The evidence is so clear and unambiguous that life is not the product of simple chemistry and physics, but it's the product of an engineer and artist working in a dramatic intervention in nature. And a lot of people have a problem with the term intervention, and the bottom line is they have to get over it, because that's reality. So let's talk about the science. That felt good. Okay. So, when you talk about the origin of life, the question is, how did the first cell come into existence? There's lots of different theories, but most of the theories are going to include these basic steps. At some point, you've got to get the basic building blocks of life. You've got to get amino acids, because amino acids are what produce proteins, and proteins are the main brick and mortar of your cell. You also have to get things like nucleotides. Nucleotides are like what produce RNA or DNA. DNA is where you contain the operating system for life, the instructions for reproducing things. What has to happen is after you get these building blocks, they have to form into large molecules, long chains. Proteins are like several hundred amino acids in a chain, a lot like letters in a sentence. There are 20 amino acids that form proteins. In the same way, there are 26 English letters that form sentences, the same basic idea. DNA is formed of nucleotides, which are 4 letters, A, C, T, and G. Those are the 4 letters of DNA, A, C, T, and G. And then RNA, the T becomes a U. It's the same basic idea. What happens eventually is you have to get a cell membrane. A cell membrane is basically the vesicle that is what surrounds all of your metabolism. It's basically your wall to your cell. It's the boundary between what's on the inside of the cell and the outside world. And that's typically made of what are called lipids, which are complex chemicals. Eventually, you have to have a genetic code because you have to have information in DNA because DNA is like the operating system for the cell. It's what allows a cell to function. The DNA includes the blueprint for all the parts. So if you want to make a new part, you go to DNA. DNA has the information of how to produce a part. So what happens is the information in your cell is encoded into DNA. In the same way, if you have a computer program, any computer programmers in here? Yeah, I figured there'd be more of that in artists. That's cool. What happens if you type letters into a computer, like the instructions for an Excel spreadsheet, each letter gets converted into what 2 numbers? 1s and 0s. So you have the information in a computer program that's encoded into 1s and 0s in your hard drive or in your operating system, in your RAM. And what happens is the same thing in life. You have not 1s and 0s, but A's, C, T's, and G's. So you have to have a genetic code. And eventually you have to have a metabolism. And metabolism is simply all the functions and processes that build your parts and run your cells. Now, there's a lot of different theories of what order it came in, but that's the basic steps of how do you get a cell. Now, the question is, how far have scientists gotten in figuring out how this could have happened? Well, really, if you look at the first step is obviously to get the building blocks. So when you look at the origin of life research, the most famous experiment early on was the Miller early experiment. Like basically you've got this flask of methane, ammonia, and hydrogen, you shock it with electricity, and you create some basic building blocks of life, some basic amino acids, maybe a few other things. That was the high point of origin of life research. I mean, this was front page news around the world. Scientists create the building blocks of life. There was a problem though, because everything went downhill from here. Because what people realized is that the gases used in this experiment were not the gases on the early Earth. So when they redid the experiment with the correct gases, they didn't really get anything of significance. If they cheated a little bit, you could get glycine, maybe a few amino acids, but essentially you got very much just a handful of the products of life. Plus, even with the original experiments and with the newer ones, you didn't just produce a few amino acids, but you produced a whole lot of other organic compounds. And the problem is these other organic byproducts would interact with your organic amino acids and would cause the origin of life to cease. It prevented anything from moving forward. You would never get chains, you would never get you get nothing. You get tar. Like at the bottom of your barbecue pit after you have a nice burger. See, I'm bringing it down. See that? Just make it accessible. We all know the tar at the bottom of your barbecue. That's what you see in these experiments. So this has been a big problem. So what happened is a lot of origin of life researchers switched strategies. Instead of trying to use realistic experiments to see what nature could do, they produced incredibly complex experiments with multiple steps to create things like the precursors to nucleotides. So in these experiments, you basically have a perfectly set up experiment with the right conditions, the right chemicals, the right catalyst, the right temperature, light at a specific frequency at a perfect intensity. And then after all that, you get a little bit of something you want. So you take that little bit of a product and then you purify it and you multiply it and you start with a gallon of the new stuff, I'm exaggerating. And then you create new conditions, new catalysts, new pH, new conditions. And then you let that run and you get another little bit of something you want. So you take that, you purify it, you concentrate it, you get a lot more of it, and then you keep doing this step by step by step. Needless to say, this is completely different from what could possibly have happened on the early Earth. It's not even remotely similar. In fact, there was an organic synthetic chemist named James Tour, and he realized there was something very suspicious because he creates molecular machines. Like, this is a car he created out of molecules. It's actually the fastest nanocar in the world. It can go like a few micrometers in a couple hours. It's truly amazing. He created these molecular submarines. And what these molecular submarines do is they'll actually attach to cancer cells, and they'll start to burrow into that cell, and they'll kill the cell. Absolutely amazing. But to create these molecular machines requires page after page of very detailed protocols of changing conditions, changing chemicals. It's very, very difficult. It's the sort of thing that you win a Nobel Prize for. So he said, this origin of life research looks very suspicious. So he looked at the articles, he called up the top professors in the world that do origin of life. He realized that they don't have a clue of what's going on. Like, they have no idea how to produce the basic building blocks. They have no idea how they came together. They have no idea how to get, a functional cell membrane. So basically, origin of life hasn't advanced one step for the last 65 years. We're really back at the Stanley Miller experiment. Now, how many of you have ever seen headlines on newsprint if you happen to be over 50, or you happen to be watching Yahoo News? How many have seen news lines like, origin of life researchers have huge breakthrough. They solved this problem. New theory. It's all nonsense. It's all exaggerations. Because when you actually look at the research, what happens is anytime they're successful, they have to use so much intervention, so many careful protocols, that it has no relevance to what would have happened on the early Earth. In fact, this was realized by a very famous origin of life researcher, Robert Shapiro, and he said, the analogy that comes to mind is that of a golfer who, having played a golf ball through an 18-hole course, then assumed that the ball could also play itself around the course in his absence. He had demonstrated the possibility of the event. It was only necessary to presume that some combination of natural forces, earthquakes, winds, tornadoes, and floods, for example, could produce the same result given enough time. That's a beautiful analogy. He's an origin of life researcher, a very, very famous one. Now, that's a serious problem, that what 65 years of origin of life research have demonstrated over and over again is molecules never move towards life naturally, not without enormous intelligent intervention. That's what we see. Now, there's another problem that very few people talk about, and that's the localization problem. Because if you have, let's say, 1 cubic meter of water, 1 cubic meter, and in there you have a beautiful cell membrane perfectly designed for life, and you have another protein that's necessary to run the cell. How long would it take through diffusion for these two things to make contact? And diffusion has to be the main search mechanism. That's just the things moving around sort of randomly. Because if there was such turbulent water that you could accelerate the process, you'd eviscerate your cell. So you're talking about diffusion. It would take millions of years before they would even make contact. So long before this protein could find this cell membrane, it would break apart, it would denature. Now, we're not talking about just a cubic meter, because the chemical conditions needed to produce the different building blocks of life are very, very different. So, for instance, a nucleotide, to get the base and to get, let's say, the sugar, you require different chemical conditions. And if you try to do it in the same place, the chemistry poisons itself. It can't happen. So you have to have these different building blocks form in different parts of the Earth, somehow migrate to the same small environment, and then migrate inside of a cell membrane. So you're talking about billions, if not trillions of gallons of water, cubic meters of water, in order for this to find itself. It's never going to happen. And this is a problem that no one talks about. Hey, I'm going to ignore these problems and talk about an even more fundamental issue. And that's the thermodynamics. Here's where it gets really serious. Now, before we get to that, I want to talk a little bit about how people have thought about the origin of life historically. And one of the great challenges is the issue of probability. Because there was a famous physicist I've mentioned, Fred Hoyle, and he asked the question, if you've got, let's say, a tank of water, and you have all of the building blocks of life you want, all the amino acids, the nucleotides, whatever you want, whatever conditions, it's Christmas, take your pick. The question becomes, how hard would it be for these chemicals to come together to form a cell? He calculated the odds of it happening would be roughly 1 chance in 10 to the 40,000. That's a 1 with 40,000 zeros. So if you have these chemicals randomly interconnecting, the chance of that producing life would be 1 in 10 to the 40,000. He compared that to the chance of a tornado going through a junkyard, throwing all the pieces of debris up in the air, and having a 747 airplane land filled with gas ready to fly. That's a problem. Now, what happens is people often associate the idea of probability with what's called entropy. That's a science word. Don't panic. It's okay. What's entropy? Well, entropy is very closely associated with probability, because the entropy of a system is simply telling you how many ways that system can come into being. So let me use an example. Here you've got 2 containers that are interconnected. You've got 4 molecules, and what happens is you can either have 4 molecules on one side or the other, 3 on one, 1 on the other, or 2 and 2. How many ways could you have 4 molecules on one side or 4 molecules on the other? How many ways can that happen? 2. Yeah, that's not a rhetorical question. You can answer. That's kind. There's 2 ways that happen. Now, what about 3 and 1? Is there more ways to have 3 and 1 than 4 and 0? What about 2 and 2? So there's a lot more ways to have 2 on one side and 2 on the other. Therefore, that state has greater entropy. It's more probable to take place because there's no more ways it can happen. That's all entropy is. A number of ways something can happen. Not terribly complex. It gets more detailed if you get into the math, but that's okay. So many people have said that the origin of life is not possible because life represents a low entropy state or a highly improbable state, and nature doesn't do that. Nature goes from order to disorder. That argument is not complete. And let me explain to you why. Ice. Does ice more ordered or less ordered than water? More ordered, right? So what has more entropy, ice or water? Water has more entropy. There's more ways you can have molecules of water. Yet, do you, and you can answer this in Ontario very easily, is it possible for water to become ice spontaneously? Yeah. Yes. Yeah, I'm from Florida, so it's not as obvious, if you ask that, but here it's quite obvious. So what happened? Does that mean entropy is messed up? No. The reason water becomes ice is because you've got an attractive force between the oxygen and the hydrogen. So ice represents a lower energy state than water. So what happens is not all configurations of matter are equally probable. That's the key. Before, when I was talking about entropy, I was assuming everything was equally probable, but not everything is equally probable. Let me use an analogy. If I came to you and you didn't know me, and I have a pair of dice, I said, I bet you $1,000 I can roll 1,000 sixes in a row. Who would take me up on that bet? Raise your hand. You would lose. Why? Because the dice are loaded. See? I'm not stupid. Come on, I have a PhD. In the same way, nature wants molecules to go into a state of lower energy. That's where the dice are loaded. But now here's the problem. Life represents a state of very high order, very low entropy. But it also represents a state of very high energy. There's lots of energy in those chemical bonds. That's why we eat food to live. So getting life is kind of like rolling 1,000 die, but the die are loaded against rolling 6, 1,000,000,000 to 1. That's the challenge. So there's actually a very serious problem because all natural processes either go to higher entropy or lower energy or both. But nature has to do the exact opposite. Now, if you happen to be a chemist or a physicist or a biologist, what you know is scientists will often combine the entropy and the energy into what's called the free energy. The free energy is the measure of energy that's useful for doing work. That's free energy. Like a battery has lots of free energy because a battery can run your toy or your pointer or whatever. There's lots of energy in the air with molecules bouncing around, but can you use that energy in the air to run your car? No, it's not free energy. There's lots of entropy. So free energy is the amount of energy that's useful for doing work. So all natural processes go from high free energy to low free energy, but life requires nature to take a bunch of chemicals to go from low free energy to high free energy. That is a physical impossibility. In fact, there was a professor, a biophysicist named Harold Morowitz, and he said the probability of some chemical soup on the early Earth absorbing enough heat from the environment to form a cell is roughly 1 chance in 10 to the power of 100 billion. That's like an E. coli cell. That's like a 1 with 100 billion zeros on it. And just to give you some context, the smallest probability that can happen in theory is 1 over a 1 with 150 zeros. If it's more improbable than that, it can't happen. This is 10 billion zeros. Not going to happen. So what happened is people have realized that life cannot form under normal circumstances. And when I say normal circumstances, that's like you've got lightning that hits a pond, it stirs up all the chemicals, and then they settle down into some state. You'll never get life like that. But they said, what about if we just add lots of energy? We just shove this thing full of energy, and then maybe what'll happen is if you move it far from equilibrium, you'll then get life. Well, there's some precedent, like if you heat water from below, you're going to get roll patterns. It's sort of order formation. Tornado cloud, it's called self-organization. Maybe you've seen the BZ reaction when you get pattern formation. So the hope was maybe in a system driven far from equilibrium, like sun is just pouring down energy on a pond, or you have a thermal vent, you can get self-ordering life. The problem is what happens in these systems is everything that happens in these systems is the opposite of what you need to get life. So if you've got a high concentration of chemicals, it's going to diffuse and spread out into low concentration. If you've got a homochiral mixture, meaning that you've got, let's say, an amino acid of only one-handedness, because amino acids will have either a left-handed or a right-handed version, only one is useful in life. So if you only have a homochiral mixture, it'll turn into a mixture with both versions. Chemical reactions will go from high free energy to low free energy, but life needs the exact opposite. And most importantly, very large high energy molecules tend to break apart into smaller lower energy molecules, but life requires small low energy molecules to form very big energetic molecules like RNA, DNA, and proteins. That's a big problem. So every natural process does the opposite of what's needed to get life. That's why the order in self-organizing systems that are driven far from equilibrium is quite different from the order in life. Oops, sorry about that. That's better. So instead of having these dynamic patterns like a tornado cloud, you need structural order in chemical bonds with molecular machines. While these systems, you get order macroscopically, like a tornado cloud, you have microscopic increases of entropy. With life, you need the opposite. With these far from equilibrium systems, they still go towards lower free energy, but life, you have to go to higher free energy. And what happens is the law-governed order is how you describe a tornado, but with life, you have specified complexity, which means you have very specific arrangements of molecules that transcend the physics and chemistry. In the same way, you can't explain a car by the physics and chemistry of plastic and metal. You can only explain it by the blueprint. It's the same sort of order you see in life. You have blueprints. And of course, there's been more sophisticated analyses by people like Jeremy England in MIT. And Jeremy England has talked about what are called fluctuation theorems. And a really interesting story is people said that Jeremy England came up with a new physics theory for life, that somehow physics can explain the origin of life. Who's seen that article? A few of you? The wrong crowd, that's fine. Again, I never trust what you read in the press. I go back to the original literature. When you look at England's equations, it basically disproves all origin of life theories. Because when you actually look at his math, what it shows you is in systems driven far from equilibrium, they tend towards greater entropy. The internal entropy increases, and they tend to give off heat. Well, again, the origin of life requires the opposite. So based on his equations, what happens is the probability of life forming away from equilibrium is just as small as near equilibrium. What that means is the origin of life, trying to argue that life originated through natural processes, is like trying to create a perpetual motion machine or to market alchemy. It's a scientific impossibility. So the question is, how does life come about? Because cells reproduce, right? How does that happen? Well, any of you see the Avengers? Remember when what's his name? Dr. Strange says, one way to defeat Thanos, one way. In the same way, there's only one way to overcome the thermodynamics. How many ways? One way. And that's with information and machines. So let's talk about that. And I'm going to use an analogy. Now, remember, whenever you read Origin of Life researchers, you always hear you just have to add energy and you create order. You hear that all the time. But let's use an analogy. How many of you ever come home and basically your house has been a total mess? Either it's your husband's fault, your kid's fault. Okay. And you think to yourself, I've heard that energy creates order. That's awesome. So you take gasoline, you pour it on your couch, you set your couch on fire. We've got energy. Let's watch my house. Is that going to work? No, it's probably not going to turn out well for your house. So you think, okay, what I need is machinery. I need a robot. Because with a robot, what you can do is it has an engine. And what that engine does is it takes gasoline or electricity or some other form of energy. It converts that energy into mechanical work, right? So you can do work to clean up your house. So let's imagine you buy your robot off eBay or off Amazon or whatever the Canadian version is, and you plug it in, you charge it up, you let it run in your house. Is that going to help your house? Most likely not. What did I forget? What does my robot need? Instructions, information, programming, and then you can clean up your house. So it's the same thing. When you look in a cell, what happens is if you have, let's imagine that you have an advanced alien race, they come to Earth, and they create a cell, but they have to go back, they're being invaded, so they only create 90% of a cell. So they take that 90% of a cell and they put it on Earth. Guess what's going to happen? It's going to move right back towards equilibrium. All the chemicals will break down, so it's going to move away from the final product of life. Because what do you need? A cell has to have an engine. Because what an engine does is it takes some form of energy, like glucose or light, and it converts it into high energy chemicals, like ATP, and those are the molecular batteries that run the cell. They power the chemical reactions. They power the active transport that pulls in nutrients and gives off waste. So you have to have engines. And cells have very complex machinery like ATP synthase, they have the plastids and so forth. So they have incredibly complex molecular machinery which can process some fuel and produce high energy molecules. That's how cells work. The problem is at the origin of life, that machinery did not exist. The only way to get that machinery is with a cell to build it. That's a problem. Now, various scientists have tried to think, well, what if we have some natural process that can act like a molecular machine? A classic example is Nick Lane. He imagined a hydrothermal vent where you have protons going through some channel that produce maybe some chemical reaction. The problem is, when you look at the amount of energy needed just to maintain a cell, and prevent a cell from breaking apart, it's about 1 watt per gram. So the energy production of a cell is like a high-performance sports car. That's the type of power a cell needs just to stay alive. While if you look at these experiments, you get about a nanowatt per gram. That's a billionth of what's necessary just to prevent a cell breaking apart. And of that energy produced, it's in the form of what's called formaldehyde, which is completely useless for helping a cell move forward because the concentrations are too small. So in other words, 0% of that nanowatt could help towards the origin of life. Let's put it simply. Believing that some natural configuration of molecules will create that type of machinery to produce that type of energy is like a tornado producing a jet engine in a junkyard. It's not going to happen. But even if it did, even if we assume there was all the high energy molecules, all the engines, it still wouldn't help. Why is that? Because a cell consists of very, very complex molecular machinery, which require very specific chemical reactions that take place in a very carefully timed fashion. The chance of a random set of chemical reactions producing anything comparable to life is unimaginably small. Like almost all origin of life researchers acknowledge it can't happen. Plus, the chemical reactions in life require different chemical conditions, different chemical products. They require different pHs. Some require water, some don't. So it's an impossibility for these reactions to take place in the same location. So what does a cell do? Well, a cell uses what are called enzymes. Remember I talked about those proteins? Remember, a protein is a long chain of amino acids. And what happens is that long chain of amino acids has to be in a very particular order such that that chain of amino acids folds up into the right three-dimensional shape, and then that enzyme will drive the right chemical reaction. And that enzyme will also take energy from ATP or some other chemical. It'll direct that energy to drive the right chemical reaction. That's how life does it. Remember I talked about how in your robot you need instructions? How each line of instruction will say, sweep the floor, wash the dish. In the same way, the information in these proteins is the information that will tell the cell how to operate. It tells what reactions need to take place. So that's what you need, is both information and machinery. We'll skip that. So that's what you need for life, is information and machinery. Now, why is that significant? Well, let's imagine that you're feeling kind of sick, you go home, you tell your spouse about this, your mother, and what happens is you kind of go upstairs and you come down and she prepares you, or he prepares you, a really nice bowl of alphabet soup. If we had alphabet soup, yeah, don't you love it with the letters? And if you're a child, what do you want to do with your alphabet soup? You want to stir it up, and what do you want to see? You want to see words, right? And maybe if you see your name, it's like Bob, it's a sign from God, right? No. Because Bob is a very short word, so it's not that improbable to get a little bit of information. But what if you see the words, drink plenty of fluids and rest until you're feeling better? Now, if you saw that, would you conclude, I think I can explain that through the chemistry of the pasta? If I just know more organic chemistry, one day we'll know how chemistry of pasta can produce letters. Sentences. Or maybe it's the physics of the boiling water. Won't that explain it? Or is saying that information makes sense, or is that the concerned parent of the gaps fallacy? Is that just giving up on science to say that that was produced by some intelligent agent? No, because when you see large amounts of information, you know you are dealing with intelligent agency, because information is something that transcends the physics and chemistry of the letters. It doesn't matter what this pasta is made from. It doesn't matter if it's Scrabble letters or pasta or computer code. The information uses a medium, but it's beyond the medium. Information, at least large quantities, is only a product of the mind. That's key. Now, what happens is the question becomes, well, is that a fair analogy? I mean, can you really compare the sequence of letters in a protein to an English sentence? Well, apparently you can, because if you look at the latest research, experts in proteins recognize that in the same way letters form words, in proteins, amino acids form what are called domains. Those are like independent folded units. And in the same way words become sentences, domains in a protein form the entire three-dimensional structure. So you have syntax, semantics, grammar, context. Now also, when you look at the rarity of proteins, they're extremely rare. Like Doug Axe is one of my colleagues. He's done research that he talked about in the book Undeniable. And he determined what is the probability of a random amino acid sequence forming a functional protein. In fact, he was only looking at one small part of it, like 153 amino acids. The chance of a random set of amino acids forming a domain which is 153 letters long is 1 chance in 10 to the power 77. That's a 1 with 77 zeros. That's kind of like if you've got one marked atom in a million galaxies, the chance of you picking that atom is a chance of a random sequence forming a functional protein. Now, what you find in this research, and this is some research I've looked into, is here's the beta-lactamase protein. Don't worry about what it is. It's a protein, just trust me. And this shows you, as you have more and more changes of letters, mutations, what percentage of these proteins will actually be functional. So this would be 1, 2, 3. So after about 3 mutations, 3 changes of the letters, it's no longer, half are no longer functional. Roughly, where do you think this drops to 0? What number would you say it drops to 0? Okay, yeah, somewhere 10, whatever, somewhere in here. That's 10% of the protein. So almost no examples of these proteins with 10% of the letters changed are functional. 10%, why is that relevant? Okay, I want you to raise your hand if you can recognize this paragraph. Okay, ready? Okay, tell me when you recognize this. Okay, good. Any more? Yeah, very good. It's Mary had a little lamb. Now, I've only changed 10% of the letters, but it's still readable, right? You change 10% of an English sentence, it's still readable. You change 10% of a protein, it's completely non-functional. That tells you that the probability of a random sequence forming a functional protein is less than a readable paragraph. That's how rare these things are. So it's a very good analogy. Now, also, what's interesting is there's been researchers that have looked into what is a minimally complex cell. Like how much can you pare back the parts of a cell and it still functions? And what happens, they've looked at like mycoplasma, they've looked at these different cells, and they've said, okay, it takes a certain number of genes for this thing to function. Also, people from NASA have looked at what are the minimal components necessary for a self-replicating machine. And that was also somewhat based on the theoretical work of von Neumann of self-replicators. These 2 lines of research have converged. And what you find is if you want a cell to work at its most basic level, you need information processing, error correction, energy production, manufacturing, auto-assembly, feedback control loops, global control of the system. And if you look at all that, the amount of information needed for a minimally complex cell is comparable to that of the information in A Christmas Carol. That's what's necessary. You can have a perfect cell, but you're missing one essential protein. What happens? The metabolism stops, it breaks apart, and turns back into simple chemicals. So what you find is undeniable evidence of design. Because if you asked yourself, in what other contexts would you find a nanotechnology machine capable of information processing, energy production, et cetera, you would not have any doubt it was designed, right? Now, a lot of people will say, no, design is unscientific, you can't do that. It's just against science, it's giving up on science. But let me use an analogy. Who's ever seen the movie Contact with Jodie Foster? Great movie. Now, Jodie Foster, she was looking at these signals from space. She found the signal, and the signal contained the schematics of a spaceship. Now, and of course, that was the whole point of the movie, is these aliens have sent a signal to Earth. Now, what would happen if Jodie Foster's associate said, Jodie, you are so unscientific. You cannot conclude design from this signal. We can only look at natural mechanisms. I think it was produced by quasars that were self-replicating. And they were being selected for spaceship-emitting signals. No, that's foolish. In the same way, when you look at life, you see undeniable evidence of foresight, coordination, goal direction, information. So the evidence for design is undeniable and irrefutable. Thank you.